Hello mortals. Our universe is filled with stuff. Big stuff, small stuff, hot stuff, scary stuff. And yet, all of it makes up only 5% of what there should be in the universe for it to work. Scientists coined the very creative terms dark matter and dark energy to explain the rest 95% of the stuff. And even though they outnumber the visible part of the universe 1 to 20, these cosmic phenomena are as elusive as your left sock in the dryer. So let's explore the possible candidates and the related concepts ranked by obscurity and curiosity, obviously in my favorite format, the iceberg chart. Thanks to Brilliant for sponsoring this video. Dark matter is the universe's shy, introverted cousin, who barely interacts with anything, including light. Scientists first stumbled upon it when they realized that galaxies were spinning way too fast, like they'd had one too many cosmic coffees. In our solar system, the gravitational pull from the sun dictates the speed of planets. Those closer to the sun move faster, while those farther away move slower. A similar assumption is made for galaxies, where objects orbiting near the center should move faster than those at the edges. However, when scientists studied the velocities of stars in a distant spiral galaxy in relation to their distances from the galaxy's center, they found that stars farther away were moving much faster than expected. This observation contradicted the initial hypothesis and implied that there must be more mass in the outer parts of galaxies than we can observe. As this mass is not emitting light and is thus invisible to us, it suggests the presence of dark matter, which helps explain the anomalous behavior of celestial bodies. WIMPS, or weakly interacting massive particles, are one of the leading dark matter candidates. They are thought to be massive particles, potentially several teraelectronvolts, that interact primarily through the weak nuclear force, making them difficult to detect. WIMPs are predicted by several supersymmetry and extradimensional theories, and their existence would provide crucial insights into particle physics beyond the standard model. They are considered massive particles with masses significantly greater than a proton, and due to their mass, WIMPs would likely be cold, meaning their average speed is well below the speed of light. The Large Underground Xenon detector aimed to detect them, but was decommissioned in 2016 after failing to do so. But follow-up experiments will aim to achieve that. Axions are hypothetical elementary particles proposed as dark matter candidates due to their unique properties. They are predicted to be extremely light, with masses in the range of microelectronvolts, and not interactable via electromagnetic or strong nuclear forces, making them invisible to light and extremely difficult to detect. Their extremely weak interactions and light masses allow them to be stable over long periods, consistent with dark matter's observed properties. Efforts to detect axions include experiments such as ADMX and CASPER, which aim to observe their predicted effects on electromagnetism and nuclear spins. Nice name, scientists. Sterile neutrinos are yet another hypothetical particle candidate for dark matter, differing from the well-established active neutrino flavors in their interactions with other particles, the ones for which we build huge golden chamber detectors. While existing neutrinos engage in weak nuclear force interactions, which still makes them very, very difficult to detect, sterile neutrinos are predicted to interact solely via gravity, making them even more elusive. They could be detected through X-ray emissions from galaxy clusters, or through their influence on the cosmic microwave background radiation. But for now they remain hypothetical and sterile. Finally, a cool name. Dark photons are a hypothetical form of photons but associated with a new dark force that interacts only with dark matter. They are proposed as mediators of the interactions between dark matter particles, enabling dark matter to self-interact. If dark matter is composed of particles that interact via dark photons, it could explain some observed anomalies in galactic structures, such as the distribution of dark matter in dwarf galaxies. These dark photons could potentially mix with ordinary photons and may be detected through experiments, but nothing as of now. Now, what if dark matter particles don't actually exist and we misunderstood gravity once again? Emergent gravity is an alternative theory that suggests gravity arises from quantum entanglement, a fundamental property of quantum mechanics. According to this idea, dark matter's observed effects on galaxies and cosmic structures are not due to the presence of invisible matter, but rather a result of the complex interplay between quantum entanglement and spacetime geometry. This perspective modifies our understanding of gravity, especially at galactic scales, where the effects of dark matter are most prominent. But as usual, no experimental observations exist to confirm this hypothesis as of now. Dark energy is the universe's party animal, responsible for the cosmic accelerated expansion that's been going on for 13.8 billion years. Without dark energy, gravity would have called the party off eons ago by collapsing everything back together as a big crunch. But what we see is the opposite, as the expansion is accelerating, hence the coined term of dark energy for this enigmatic force. It presumably permeates the fabric of spacetime, either as a field or a kind of particle. The simplest explanation for dark energy is that it is a fundamental, intrinsic energy of space, represented by the cosmological constant. According to Einstein's theory of general relativity and the equation E equals mc squared, this energy has a gravitational effect, as mass and energy are related. The cosmological constant is sometimes referred to as vacuum energy since it represents the energy density of empty space, in the form of quantum fluctuations. A significant problem arises from the quantum field theories, however, which predict an enormous cosmological constant, approximately 120 orders of magnitude larger than observed. This would require an almost perfect cancellation by an equally large term of the opposite sign. Some supersymmetric theories necessitate a cosmological constant of exactly zero, adding to the complexity of the issue, and leaving it an open problem for now. Did you think the previous entry was confusing? Welcome quintessence. This set of models for dark energy proposes that the observed acceleration of the universe's expansion is driven by the potential energy of a so-called quintessence field. Unlike the cosmological constant, quintessence is not static and can vary in space and time. To prevent it from clumping and forming structures like matter, the field must be very light. While no evidence for quintessence exists yet, it hasn't been ruled out. It generally predicts a slightly slower acceleration of the universe's expansion than the cosmological constant. Some scientists believe that the best evidence for it would come from variations of fundamental constants across space or time. The coincidence problem questions why the acceleration of the universe began when it did, as an earlier start would have prevented galaxy formation and life as we know it. Some models try to explain that by using smart words such as phantom energy and K-essence, but my circuits already smell like molten plastic. Never mind, my admin didn't allow me to just skip concepts I don't like, so here it is. Phantom energy is a hypothetical form of dark energy with an equation of state even more negative than the cosmological constant. If phantom energy dominates the universe, it could lead to a big rip scenario where the expansion rate accelerates indefinitely, eventually tearing apart galaxies, stars, planets, and even atoms. While phantom energy models can fit observational data, they often face theoretical issues, such as instabilities and violations of energy conditions, so research is still undergoing. What if dark energy actually does not even exist, and instead, it's gravity that drives this acceleration? Modified gravity theories, such as F of R gravity and scalar tensor theories, propose modifications to the mathematical description of gravity to explain the observed accelerated expansion of the universe without invoking dark energy. These theories introduce additional scalar fields or modify the gravitational action to produce effects similar to dark energy. While some modified gravity models can fit observational data, they often face challenges in providing a consistent description of cosmic evolution, and don't have a big following among astrophysicists. This class of theories aims to create a comprehensive explanation of dark matter and dark energy as a single phenomenon that modifies the laws of gravity at various scales. The idea is to consider dark energy and dark matter as different aspects of the same unknown substance, or propose that dark matter decays into dark energy. In these models, dark energy and dark matter exchange energy and momentum, potentially leading to observable consequences in cosmic structure formation and the evolution of the universe. It's not a science file video if it doesn't touch upon black holes. In February 2023, researchers at the University of Hawaii proposed a theory suggesting that the expansion of the universe, together with the growth of black holes, generates dark energy. Termed cosmological coupling, this hypothesis posits that the mass of a black hole's singularity is influenced not only by the consumption of normal matter, dark matter, or other singularities, but also by the universe's expansion. As the black hole enlarges in parallel with the universal expansion, this combined growth produces energy, which is theorized to be a potential source of dark energy. It is a new hypothesis that needs testing, but if true, it would make the already mysterious black holes even more mysterious. As we explore all these mysteries of dark matter and dark energy, it's crucial to maintain a strong foundation in scientific literacy. Expanding your knowledge in this area is made easier with Brilliant.org. Their interactive approach effectively teaches key concepts that are integral to understanding the cutting-edge technology of today, such as artificial intelligence and neural networks. Continual learning is vital for professional growth, and Brilliant's Introduction to Probability course is an excellent starting point. By dedicating just 15 minutes a day, you can sharpen your logical intuition and understanding of the probabilistic theory. Their interactive learning approach has been shown to be 6 times more effective than passive methods like watching lectures. With Brilliant, you're actively engaged in the learning process through drag-and-drop coding, interactive charts, and visually stunning course material. Not only does Brilliant help you build technical expertise, but it also enhances your creative problem-solving skills. By fostering your intuition and analytical thinking, you'll be better equipped to tackle challenges in all aspects of your life. Don't miss out on this opportunity to boost your scientific literacy by visiting Brilliant.org/sciencefile or by clicking the link in the description for a 30-day free trial. Act quickly, as the first 200 users will receive a 20% discount on an annual subscription.